It is human to reshuffle or reorganize our life if we are unsatisfied. We change jobs or locations or even try physical transformations. Such a scenario is seen in chemistry as well. Certain sets of atoms and group of atoms try to rearrange themselves by migrating from one position to another for better stability or to change forms. These rearranged products may have a different arrangement of atoms, but they have the same molecular formula as the parent molecule. Such molecules with the same molecular formula but different structures are said to be structural isomers of each other. So, a rearrangement reaction produces structural isomers. For example, suppose an alkene alcohol or an enol functional group tries to undergo a rearrangement reaction to form another stable functional group, ketone. In that case, it is the hydrogen atom on the alcohol molecule that migrates. Still, both molecules have the same molecular formula. The transformation was in the functional group part. Such a transformation is significant in chemistry because, as we know, it is the functional group that drives the chemical reactions. The position from which the group moves is the migration origin or the start point, and the migration terminus is the location to which the group settles or the destination. The most common migrations are 1-2 rearrangement, in which the migrating group moves to the adjacent atom. Closer the better for an initial change, right? However, long rearrangements are also possible. The rearrangement reactions are of three types, depending on the number of electrons the migrating atom or group carries. The migrating atom or groups of atoms may migrate with 2, 1, or 0 bond electrons. If an atom or a group of atoms migrate with both the bond electrons, such a rearrangement is called nucleophilic or anionotropic. Why? Because the migrating group is regarded as a nucleophile. Since the migrating group carries along with it an electron pair, the migration terminus before any migration must have only 6 electrons, a sextet in its outer shell. That is, it must have sufficient space to accommodate 2 extra incoming electrons. So before the actual migration, such a sextet of electrons at the migration terminus is formed mainly by 2 methods, the carbocation or nitrine formation method. In the carbocation formation method, a carbocation forms before the nucleophilic migration and is commonly seen in SN1, E1, and Friedel-Crafts alkylation reaction conditions. Other examples of carbocation-induced alkyl and hydride shifts are Pinnacle rearrangement, Wagner-Mirvan shifts, dienone-phenol rearrangement, etc. Nitrine is an intermediate like carbenes formed by the heating of the azide. Nitrine is electron deficient and has a sextet of electrons which encourages alkyl migration to form isocyanate. Similar carbon-nitrogen migration of the alkyl group is seen in Curtius, Lawson, Schmidt, and Hoffman rearrangements. You can check out the detailed article published on curlyerrors.com about nucleophilic rearrangement reactions, the link to which I will place below. The second type of rearrangement reaction is when the migrating atom or group moves without the bond electron pair and leaves them behind, forming carbanions. Here, the migrating group is regarded as an electrophile. Such migration is called electrophilic or cationotropic rearrangement. And in the case of migrating hydrogen as H+, prototropic rearrangement. Rearrangement reactions like Fevrosky, Ramberg-Backlund, Wolff are examples of carbanions or carbenes formation. The last common type is when the migrating atom or group moves with only one electron, that is, as a radical. It was Heinrich Otto Weinland who in 1911 reported the first radical 1,2 rearrangement, a bis triphenyl methyl peroxide's conversion to form a rearranged addition product of the 2 radical species, a tetraphenyl ethane. We noticed how every rearrangement reaction involved breaking of some old bonds to form new ones. Sometimes it is a carbon-hydrogen bond that breaks, other times it is a carbon-carbon, carbon-nitrogen, carbon-oxygen, or a carbon-halogen bond. All this happens so that the parent molecule goes through some change by substitution, elimination, or addition reactions. As it said, don't be afraid of change. It is a beautiful thing. It moves things forward. So next time you see an atom or group of atoms making a move, be sure to categorize them. For more such concept overview of Introductory Organic Chemistry, Subscribe to Learn Chemistry with Sibi.